Hello everyone, welcome back. This week we're going to start chapter 3, crystalline structure of solid. We're going to explain how the atom arrange themselves and relation with the properties of material. Chapter 2, we discuss the subatomic structure, the way that atoms bind together and the chemical reaction happens. It's going to give us some bonding type, and those bond type providing some information on the material property. However, in this chapter we will be talking about the way that atoms arrange themselves. Now, atom arrangement give us some structures that we will discuss them in detail. Now, the way that we're describing structure of material, there is a term we call it crystal. So we call them crystalline material. When the atom arrange themselves in a way that they keep repeating, call them arrangement of atom in a repetitive manner, or they will arrange themselves in a way that it keep repeating, and it's going to give you a crystalline structure. In order to understand this crystalline structure, let me just show you something on a picture. Sorry. This is, we call it a crystal structure. Now if you check this shape here, there is atom arrange themselves on the top and in another layer, then the top layer is repeating, this layer also repeating here, so this layer here, this layer repeating here, again will repeat, this one will repeat itself, so this is, we call it in a repetitive manner. There is the way that atoms arrange themselves to close to each other, specific arrangement. We call this one crystalline structure. So when atoms arrange themselves in a manner, we call this one crystal structure. So why do atoms try to arrange themselves? To have a minimum energy at the state they are, to have a minimum energy. We'll show this one on the graph. Now beside crystalline, there are other terms that we will have. Single crystal means that, now before single crystal I have to explain polycrystalline, then I'll come back to single crystalline. Now polycrystalline, poly means multi-crystalline. Now this happens in many metals, or most of the time that we have polycrystalline. What does polycrystalline means? It means that the arrangement of atom, it is not the same inside the material, inside the entire material. Yes, we have arrangement, but not the same arrangement throughout all the material. We call this one polycrystalline. In a city, for example, imagine this is a neighbor. Look at inside this neighborhood. The houses are arranged all in the same order. Yeah, those are crystal structure. The arrangement are crystal, all of them. But the different neighbor, they are not the same. In this neighbor, the arrangement is different, but still arranged. Again here, different arrangement. Here, different arrangement. Each of them are crystal by themselves. Why the arrangement, all of them are, for example, inside here, the way that they arranged are repetitive. Inside, for example, inside here, repetitive. This is, we call them polycrystalline. Multi-small crystals you have. Small crystals together, he called polycrystalline material. And many materials in an order, they are in a way that to be polycrystalline. Why? Because single crystal means that It is exactly the same pattern repeating all over, and it is hard for a material to be single crystal. Single crystals happen naturally, but under a perfect environment. It happens to be single crystal, but it's very rare materials. In the lab also can be created, but it needs an environment, perfect environment for the atoms to go exactly the same arrangement throughout all the material. It's not like this. Imagine you taking one of them, it's the same manner repeating it, but exactly the same way. So it's not gonna have any other direction. It's not like this. This is, we call them, take one of this, for example, take one of this one. Let's say take this one here. Sorry. Take this one here. For example, let's take this one here, and imagine it all the material, it's having exactly the same way. So I cannot draw it in this way, but let's say that there will be something like this, all of it having the same arrangement exactly. Well, supposed to be symmetry, but I don't have access to make it symmetry, but it's exactly the same way, exactly the same way. This is, we call it single crystal atom. In, I mean, entire extent of the material is the same arrangement, single crystal. Now the lack of this crystallinity, if the material or the atoms does not arrange themselves in a symmetric way or in a periodic, in a repetitive manner, we call this one non-crystalline, or we call them amorphous. So amorphous is another term to represent non-crystalline material. Disordered, they are not ordered. An example, this is crystalline. Look at it, for example, the arrangement, this is repeating themselves, all of them, they are in a manner that it is repetitive. So if you continue, take another, it's going to continue in this manner, continues the same arrangement. However, non-crystalline, which called amorphous, look at them, they are not, you cannot see the pattern that those atoms arrange themselves. By the way, this is SiO2. When we explain silicon dioxide, this is glass, this is quartz. It's the same chemical compound, SiO2, but this is arranged, this is disorder. This has different material, this different properties, this one has different properties. Even though the bonding is the same, the elements are the same, silicon and oxygen, but the arrangement is going to give you some properties. Now this is a crystalline, crystal shape is like this. Glass is what? It's amorphous. This is glass. SiO2, amorphous SiO2, it's a glass. So if I want to create glass, I don't want to go for the crystal, I prefer to be amorphous to give us this property. Now most of these amorphous material, they have some transparent properties. That's transparent. But if you go for the crystal, crystals, they lose this transparency. Depends on the density of and the type of color, the other things that it changes to. Lose its transparency, will be opaque. So the crystal structure is also giving us different properties. That's what we have to know. Not just the elements, no, the crystal structure also providing us some properties. Yes, you've seen this one in chapter 2, the way that the energy or the potential energy between the atoms, as we said that if the atoms are far from each other, they will attract each other. If they're too close to each other, they will repel each other. They will repel each other. We said that there is a state, we call it equilibrium state, which is the lowest energy we have it. And that's what materials, they want to be at that state. They're trying to be at that state. The distance between them to be in a state that to have less energy. Now look at this, those atoms arrange, all of them arrange themselves at a distance, which is this distance. I mean, this is interatomic distance. If you go in this manner, this is at this stage they have at equilibrium, so less energy, they will be at less energy. But here, because the distance, maybe for example far away, they will attract each other. Here for example maybe close to each other, they will repel each other, so they will not be at the same energy or the lowest energy level. That's why they prefer themselves to be at the crystal state. So energy of crystal state is less than the energy of the atomic amorphous solid. Why? Because all of them at the equilibrium point, lowest energy that the material can be, lower energy state. This is not about the configuration, it's not about electron configuration, the way that the attraction and repulsion of the forces between the atoms will be at the minimum stage in the crystal structure. Now crystal structure, before talking about this one, let me just show you some example of crystal structure. Now look at this one. I mean, you can see the pattern here. Yes, you can see the pattern. I mean, this is repeating itself in the way that, so we call this is the structure, and it's keep repeating itself. It's going to give you a nice crystal, or the wall. This is also we can call crystal. Why? Because it's repeating the same manner, Some of the examples before explaining, let's see if we have other examples. In a 3D, in a 2D, if I have some examples. Let's see. Okay, there's not many pictures inside here. I hope it makes sense. The arrangement of atoms, we call this one crystal structure. Now we have to understand some other terms. Now in this chapter, when we're talking about atom, we will consider atom to be a sphere model, and that sphere basically will be having a radius, So when we're talking about those atoms, we will consider them as a sphere, a round sphere, and having a radius for the purpose of calculation that we have it. So if two atoms are basically beside each other, close to each other and touching each other, the distance from the center to center, you can call this is 2r, radius of the atom from each sphere. Now there is another term that we will hear, lattice. It's basically representing of the arrangement of the system that those atoms are arranging themselves in a 3D. For example, if you're looking at this one, this arrangement here, we call this one a lattice system. I mean, at each corner we may have atom. We may have atom here. We're connecting the atoms together. We may have different lattice system. We will explain them in detail. But in the beginning, lattice will be used to represent the way that the atoms are arranged in a 3D. Why? Because we have many parameters that are representing this lattice. The dimension of this system I mean, it might be cube, not maybe cube parallel piped. We may have different other systems that we will explain them: hexagonal, tetragonal, a lot of other lattice system that when time comes we'll explain them. But in the beginning, imagine that in a 3D, if you want to represent a shape in a 3D, we call it lattice. You need 6 information to represent it. The three sides A, B, C, and 3 angles that will be enough to represent any 3D shapes, regular 3D shapes. We call them lattice parameters. So A, which is the side here, B, C, and alpha, beta, gamma. Those are the 6 parameters of a lattice. We call them lattice parameters. You will hear this word a lot, lattice parameter. They will tell you, okay, find the lattice parameter. They want to know the side of this crystal structure. Another term that we will hear a lot, unit cell. Now, unit cell, we said that crystalline structure is repeating itself, yes? So when we say repeating itself, there is a structure that will be used, or a shape that will be used for creating the crystal structure. Now, if you look at the tile here, I mean, it's repeating. This is the structure that is repeating. Like, for example, you have it here, here. It's exactly repeating the same. So we call this one a unit cell. A unit cell. And this, which is the wall, this is the unit cell. Look, this is the unit cell. Why? Because this wall made out of this block, and it's the same block that we keep repeating beside each other to build this crystal structure. So we call this one unit cell, the smallest unit that you can build the crystal structure with it. That's what we call repetition of a unit cell generates the entire crystal. Well, because mainly we will work with a unit cell. If we take one unit cell, is represent the crystal structure. Represent the crystal structure. Now, we said in this chapter we will deal with metallic crystal structure. Now, why metallic crystal structure? Because all metals mainly come as crystal, and their crystal structure are easy to understand, always for the scope of this course. However, there are some ceramics. Also, they have crystal structures. Sometimes polymers, they have crystal, but most of the time polymers are non-crystal structure. Ceramics, they have crystal, non-crystal, but all the metals, they have crystal structure. Now, crystal structure might be very simple and may be very complicated. So we're gonna cover only the simple one for the purpose of this course that we have. And that's why we will stick to the metallic crystal structure. They're simple to understand rather than the other ones. I mean, chapter 12 or 14 are explaining the crystal structure for ceramics and polymers. It's not the scope of this course. Now, we said that polycrystalline, as we said, that they are usually polycrystalline. Why? Because the formation of these atoms, it's hard to be a single crystal, so they will come in a polycrystalline manner. Now, it does not mean that you cannot have non-crystalline. As we said, that the rapid cooling is one of the techniques that we're using it. We're not letting the atoms arrange themselves. Imagine you you melt this material together, and you don't allow them to arrange themselves in a manner to be crystal. You put them in a water or something for example, let's say liquid nitrogen, or using gas, you just simply cooling the material. When you cool the material, they will solidify them. I mean, they will be solid and the atoms cannot move anymore. But in a melted, I mean semi-melted status, atoms have energy and they can arrange themselves. That's why if you want to get an amorphous metal, normally we'll go for rapid cooling. We're not gonna let the material to cool down in a over a long period of time, because we want it to be non-crystalline, so we cool the material fast. This is one technique that they're using it to create an amorphous material. Now the non-directional that we explain it here, the non-directional, it's gonna give us some dense atomic packing. Now the non-direct, you will remember the direction and directional bonding. We said that the way that the atoms, I mean the materials, having different properties. Here it is non-directional. How does it help us? I mean non-directional basically means that because we said that in any direction, if you look at it, the arrangement will be the same. The arrangement will be the same, so it's gonna end up a dense atomic or packing, they call it. And this is gonna give us some idea about the density of the material and how those density will be calculated based on this density, on those arrangement of atomic that we have it. So R, we said that representing the radius of atoms. They're very small, I mean nanometers, in a nanometer scales we have them, so very small, but we'll see them. Now, we're going to explain, we'll create another video. There are the type of crystal structure that we will talk about for metallic. We have 4 crystal structure. I mean, they call them the type of unit cell. Remember, unit cell is what? If you have a unit cell, repetitive unit cell, we're going to give you crystal structure. The crystal is going to give you the crystal. So the term that we have it, simple cubic, SC. We have face-centered cube. We're going to tell you why we call them face-centered cube, FCC. We have body-centered cube, BCC, and we have hexagonal closed pack, HCP. We're going to cover 4 crystal structures, 4 crystal structure for metals. We shall explain one by one, and detail of each crystal structure will be explained in the different videos. Thanks for watching.